Okay, so let's start. It's great today to have Guy David from the University of Paris-Saclay, and he will talk to us about the harmonic measure with Robin boundary conditions. I guess is it Robin? What is it? Robin. He's a French mathematician, right?
He's celebrated for studying the Fourier problem. As usually happens. Right. Okay, so very glad to be here. I was not in this place for many years, let's say. Okay, thanks for the invitation. So the thing is, I'm going to talk to you about with these people. So Marco Decio was now in ATH, Michael Engelstein, who knows, Svetlana, who you know, and Marco Michetti, who was postdoc in Orsay. And to some extent, it's also done with Marcel because he was essentially explaining the problem to us and convincing us that it can interpret. And then there will be a point where I will say that gene culture helps. Okay, so let me try to go through. Oh, I forgot to ask, 1 hour, 45 minutes, 40 minutes?
No, 1 hour. 55 minutes and questions.
Okay. So this is my problem. Laplacian equal to 0, so function is harmonic in the domain. And at the boundary, it satisfies this strange equation where it's a mixture of normal derivative and the function itself, which is supposed to either vanish, most of our cases, or be a given function f. Okay? So for instance, this would be the usual Dirichlet problem. And here I'm adding some part.
A is a number, or it depends on the point? A is a number?
A is a number, it could be a function, but let's say it's a number for a moment. And I wrote in which way the normal derivative is oriented. Let's go directly to the two simple examples. This one, R2 could be Rn plus 1 plus. This would be a solution to the Dirichlet problem, 0 at the boundary. And here, if I'm adding 1 over A, I get a solution. Okay. And the same way here, this is a function that vanishes on the sphere. And then if I add 1 over A, I get a Robin solution. And
so on the left, X is a real number.
Here,
X is a real number.
Yes. Here it's important because log is the harmonic function.
Mm-hmm.
Here you don't care.
Okay.
It could be any dimension. And otherwise you replace it by some power.
Yeah.
Okay. But anyway, just to give an idea, there are not so many cases where you can compute solutions, but at least this is one thing. And again, you can think of a function which is positive along the boundary and satisfies this equation.
Where did T come from?
Sorry?
Where did T come?
It's XY. Maybe.
Oh.
I was also confused. I was thinking like all of a sudden there's time. No, it's vertical variable.
Okay, sorry. Yes, but it's a written view of xt. So I'm still not guilty, except maybe of bad choices. Okay. Harmonic measure. So harmonic measure is this measure that has possibly a definition with Brownian motion, which we'll talk about, but here the harmonic measure is the measure that gives you solutions. So in other words, you take a function on the boundary, you solve this equation here, okay? And the harmonic measure is the thing against which you integrate the values of a function at the boundary to get the function the values of a function in the middle of the domain, okay? Or if you just want a definition, you just solve this thing here, where your Robin function f is the characteristic function of a set in the boundary. And then if you can solve this, you can solve this. Okay. There is a maximum principle. I mean, some of the things are wrong for this problem, but at least there is a maximum principle and things like this, so don't worry too much. And it's linear. Okay. It's hard not to talk about the Brownian interpretation of those things, but unfortunately, it's going to be less neutral. So let's say you pick a point X, you start Brownian motion here. At some point of time it hits. You count 1 if you were in the set E that you were computing the harmonic measure of, and you count 0 if you land outside, and that's the Dirichlet harmonic measure that you all know. And for Robin harmonic measure, you have to imagine that in fact, instead of being absorbed the first time, when you hit, there is some probability that you will bounce, or you will just start again from this point, and then go maybe back to the boundary, and eventually you'll get absorbed, and this will be the probability of being absorbed in E the last time, the only time you were absorbed. Okay, and I'm cheating a little bit because if I were saying things like this, it would be false, because when I'm at the boundary, the chances of hitting the same place at the boundary are enormous. So either you decide that you do random walks and then make an analog, or otherwise you'd have to study local time of Brownian motion at the boundary, which you do as you like, but I'm afraid of doing that. Okay. And again, I had this comment saying that Robin was celebrated in France for.
So when you're saying you're doing a random walk, so you mean you discretize the time?
Yeah, if you discretize, you don't have this issue of.
This issue of sort of staying there.
It's just, I do not know how to say when I start from a boundary, the probability of being absorbed is
Okay.
something, because I won't go very far, right?
Yes,
So it's just, and
exactly.
doing a random walk would be a way to really assign a probability of being absorbed each time I hit. And then otherwise I continue my random.
And so when you do a random walk, it means you discretize the times.
Yeah, I
And then you compute the
discretize times, I
probability.
discretize the domain,
And then you let the discretization to
and I
zero.
would land, yeah, but it would be complicated too. So it's just, as usual, we like to say things about harmonic measure and Brownian motions. And whenever we prove theorems, we actually prove theorems with analysis and functions
And so for the
and
harmonic
barriers, right?
Mhm.
But it's just that it gives you an idea of, again, since you're allowed to bounce, there are things that you can try to do, and it's not completely clear that it will work anyway. Let's say with Dirichlet harmonic measure, you try to make Brownian motion go in the middle of this part of the domain. It's going to be hard. It's very unlikely that it will go through. If you have a chance of bouncing a few times, maybe you're going to be able to go in this region because of that. At least you should expect that because you're not absorbed the first time you hit, you have a chance of going a little bit further in the string, in the domain, right? And this is an intuition that we use. Okay. Again, I mean, usually it helps us to think about Brownian motion, but then no proof contains Brownian motion. These are pictures of lungs of rats. This one is hard to, but at least it's at about scale 1. These are tiny details. These were given to me by one of my colleagues who was, so the credits are here. The colleague is Bertrand Henry, and they had this big synchrotron in Grenoble that they wanted to use, and they decided to do tomography of lungs of rats. And I think this does not look so impressive, but I think what happens is that you're looking at a tiny detail. And the global picture is something else. Okay. Bertrand has also a model of lung of a rat in his office, done by, what's the name? 3D impression.
Cassie, what do you mean using local time? If you have
Imagine the boundary is just straight, because this is the only case I can do local time. When I hit here, and I'm here, and I start again, I go epsilon distance, and the next time I will hit is going to be, I don't recall if it's square root of epsilon, but it's going to be very small. So I will be, if I hit the first time here, and if I try to use a probability, as I said, I will essentially always be absorbed at that place, okay? So in fact, what happens is that you can try to measure how much time the Brownian motion spent on the curve, and you use this to define harmonic measure.
You should be able to do it also with a fractal set.
Hmm?
You should be able to do it also with any.
That's part of the reason why I don't want to see, because it depends on whom you ask. My first question was, I went to Jean-François Legal because he had local times in one of his classes. And he said to me, local time in a rough domain like that? Nah. Thought it would go away. Okay. But at the same time, I found out that some people actually study local time in rough domains, but I think it's pretty dense. So, my advice is not, the lecture is going to be much easier than that. And fortunately, you don't need to understand, but there is a formula using local time that gives you an idea of what's the harmonic measure for Robin of some things. But it's, the smooth case, it's easier to use than the non-smooth case. Okay. Yeah. So I'm interested in this Robin harmonic measure that I was mentioning about, but at the same time, I think it's more interesting if you know a tiny bit about what happens in the standard situation, which is Dirichlet condition. So a function is a given function f at the boundary, and you try to solve this problem. And there is a long story. It actually happens to be much more subtle and complicated than what I'm going to talk about today, but it's good to know to start things. So here I'm saying there is a very long study of things. The first thing that people noticed is that actually they didn't even mention harmonic measure in that terms, but harmonic measure in dimension 2 for simply connected domains is just questions about the size of a conformal mapping. So if you were like the Ries brothers and you had a theorem on the size of a conformal mapping, you could translate that into an estimate on harmonic measure. Okay, so that's one thing. And then I like to say that for higher dimensions, things start with Dalberg because he's the first one that I know that had a significant absolute continuity result for, in this case, Lipschitz graphs in many dimensions. Okay. Anyway, so the question in this case, so let's think that the boundary is of codimension 1. It is reasonably smooth, but you don't know how much. And you want to know whether harmonic measure is absolutely continuous with respect to the surface measure or the natural measure there. And in this context, the answer to the question is a mixture of asking two things. First one, quantitative connectedness. That's also reasonable. If you want to have some reasonable harmonic measure here, which means if you want harmonic, Brownian paths to go all the way there, it's better if the domain is allowing you to pass through this center here. So typically in the assumptions, we add NTA. I will have a picture of NTA, but I don't want to insist so much on it. It's a way of saying the domain is sufficiently connected that this sort of thing doesn't happen. And the second thing which seems to be more important because the first one was done before is rectifiable. If the domain is flat in many places in a correct way, then there is a chance that harmonic measure will behave well. And if the domain is not flat, then typically the harmonic measure is not absolutely continuous. We'll have just two examples, but it's been a lot of work. So I feel like I have to mention this. Don't pay attention to this. We have examples instead. Okay. Right. I decided to start talking about harmonic functions. And you can also talk about elliptic functions. So you can replace the Laplacian by some other divergence form operators A, where A is a matrix which has ellipticity. And in this case, you can ask the same questions and they make sense. And it turns out that typically for the situation that I was describing above, when A is close enough to the Laplacian, to the identity, then you still have results. And if you have A which is not close, not so close, locally to the identity, then you have counterexamples. And that's more or less the situation. The situation is that people decided that they understand the reason why there should be absolute continuity, and it's a question of regularity of coefficients. Okay. Okay, and I have two main examples here. Let's returning to the Laplacian. Okay, I have two main examples: Lipschitz graphs, and for Lipschitz graphs, it is true that harmonic measure is absolutely continuous in a quantitative way with respect to surface measure, and the counter sets that I'm drawing a picture on the next page are the opposite thing. We know that harmonic measure is not absolutely continuous. Okay, no, don't hesitate to ask questions. Okay, and I'm saying, of course, I've been talking about codimension 1, but I will be interested in higher codimensions. So this is the ultimate bad set. It is known to be of dimension 1, because I took 1/4 here and 1/16 there. It is supposed to be, it is known to be totally non-rectifiable, and it is bad for harmonic measure. Harmonic measure typically likes to live on the corners and is singular with respect to surface, to the natural measure here. Okay, so that's one thing that has been known across the time. Okay, so that's the ultimate bad example normally. Okay. 2 words about NTA, just in case, but I just wave and give you pictures. NTA is a bunch of 2 conditions. Usually, we first ask that for every ball centered on the boundary, there is a ball of comparable size, which is in the domain. So the domains don't get too thin. Okay, and in addition to that, when you have 2 points in the domain, there is what people call a Harmonic chain of balls that connect. So, for instance, this is NTA, but with a very bad constant, because if you want to join this point to that point here, you have to go all the way through here. And the same way here, you have to go here. And then if you try to do that, the Harmonic chain is not going to be possible because the thing is too thin. So again, it's a way of saying your connectedness and with fit paths. Okay. This one will keep. And here is a typical statement, and I think it's good. Okay. Your domain, point of the boundary, I think it's little x, a ball. Let's pick, how many measure goes with the pole. The place of a pole is not very important, but let me not put it in the middle here. Okay. And in this ball, in this surface ball, I draw a set E, and I try to compare the harmonic measure of a set E, which is contained in what I call D probably, or B. Okay. D is the intersection. Okay. And I'm trying to compare those 2 numbers, harmonic measure of E, harmonic measure of the whole thing. And the typical estimate is assuming all the things that I was talking about, which is non-tangential access and uniform rectifiability. The ratio that I'm interested in here is comparable with powers of the ratio of surface measures. And we usually we don't know what's the optimal length. And that's what we call A infinity. No question about that? Okay, so it's just a way of saying, when I control the measure of a set E divided by the measure of a set B, I control its harmonic measure and the other way. Okay, so that's supposed to be the very good result. And that's what we look for. So, Neumann is a little strange. So Neumann is what you get when my constant little a that I was talking about, when it tends to 0. You are essentially saying that du dn is equal to 0 locally or a given function. And it's a little more complicated than usual to define, but essentially the general idea is that harmonic measure for Neumann, for a Neumann problem should be, when it's defined, just proportional to surface area. So it's supposed to be simple. Here I have this comment saying that for me, the Neumann condition is something I like because when you minimize the usual energy for Dirichlet functions, the Dirichlet norm, but for harmonic functions, and you don't put any condition on the boundary, what you will get automatically is the Neumann condition dn is to 0. So it looks like you put no condition on the boundary and see what happens. Anyway, so we claim that, I mean, in the smooth case, what happens is exactly that. Okay. That's about Neumann. Oh, yeah, I did slide. There's something amusing with this Robin problem is that it's not scale invariant the usual way. So for Dirichlet, we're used to this business that when you have a situation and you just scale the situation to half the size, nothing changes. Here it's not true. One of the terms changes and the other one stays the same, which means that if you start from a solution of Robin and you change scales, you will get a solution of Robin, but with a different value of A, which is here. So scaling changes the value of A, and it's going to be important in the estimates. Okay. Okay. It means that, for instance, what will happen to us is that when we're looking at very, very small bonds, it will be as if the coefficient A, the Robin coefficient, was tending to 0. Which means we expect that in small bonds, things will look more like Neumann solutions, and in large bonds, things will look more like Dirichlet solutions. Okay. It's amusing because, yeah. So it could be that I just went too fast in one of the slides. Of course, the question that I'm asking about is, we have this story for Dirichlet. We know it's a complicated story, and the main point is rectifiability, non-tangential excess, and smoothness of the coefficients. And I'm supposed to ask, is it the same thing for Robin? And I'm also telling you that for Robin, I should expect a little bit more smoothness because of this business about being allowed to go a little further. Yeah. Okay. And the question was, how much? At some point in time, we had these discussions with Marcel Filoche about, do we expect that when the parameter A changes, there will be a phase transition somewhere? Before that, non-absolutely continuous. After that, absolutely continuous. Or questions like this. Okay. This is okay. I'll have to explain. I think I was panicked because it's not fair, but I did not mention. I don't know. Okay. I owe you an explanation about why it's an interesting problem. But I don't know what I've been doing. I hope I didn't change my order of slides without noticing. Okay. So let me say it anyway. If once we reach the slide, which is too late, where it's a bit I'll pass it faster. So before Marcel tried to convince her that this was a nice problem, my impression was that you have Dirichlet, maybe you have Neumann, you had one parameter, you play games, and and you write papers. Okay. So I have two objections to this way of thinking. The first one is that actually in real life, you're actually solving Robin problem almost always. Right? So let me take one example. You're trying to think about the temperature in this room, okay? And Dirichlet condition would be, temperature is 0 at the walls, and you try to see what's the temperature, and maybe you put a heat source in the middle so that the solution is not 0, right? And so that's this, but at the same time, forcing temperature on the walls is probably not so easy. Neumann is you're supposing that you're perfectly insulated, and you try to find out what's the temperature in the room, and normally it should evolve in the direction of constant. And if you put a heat source, you're in trouble eventually. Okay. And Robin is essentially something saying, when it's hot on the walls, there's a chance that heat goes across the wall proportional to the heat, and things are more stable. That's one way. And the lungs is another type of problems like this. You have oxygen arriving to your lungs, and it touches the lung. And maybe the cell was supposed to absorb oxygen is not there, or is busy doing something else, or whatever. So either you get absorbed or you don't get absorbed. If you don't get absorbed, you try again some next place. And okay, and what happens in the case of a lung is that the probability of being intercepted the first time is sort of low. And what happens is that in the lung, your molecules will have many chances of being absorbed, and eventually they will get absorbed. That's okay. Sorry. Yeah, which means that I mean, the way I'm panicking, it looks like I probably will end it before I should. Okay. So this is for mostly for my fun, because my co-authors tend not to like minimizing functionals as much as I do. So here is a way to try to present a harmonic measure in a variational way. Okay, let's imagine that you're the Laplacian or your symmetric operator. Let me write down a functional, okay, for some function u. So a functional is the usual energy, so integral of a grad u squared on the domain, which is this first term. And you multiply by 1 over a, a is your coefficient, so that you normalize things correctly. And then there is a penalty, another penalty, which is the integral of the square of u on the surface. Okay, which says you try the function, you want the function u not to be too large on the surface if you want to minimize the functional, except on the set E, where when you are on the set E, you win something if the function is large. Okay, so this function u tries to be large on this part of the boundary, reasonably small on the rest, and do that with as little variation as possible. Okay. All right, why do I care about this functional? Is that, of course, it's going to end up give you a harmonic measure. So, at least in the smooth case, it's not hard to prove that this guy has minimizers, because essentially it's convex. Right? This part is beautifully convex. This one is a little convex, and this one is even affine. So it's more convex. Okay. So minimizers exist. And then you can ask, what is a minimizer? And I'm claiming the minimizer satisfies exactly the definition of harmonic measure. Okay. More precisely, you have this function u, and you compute u of x, and u of x should be the harmonic measure of a set E in the domain. Okay. Let me see if I can. Normally, I should be able to explain why. So take a minimizer. First thing is that if it's a minimizer and it minimizes this in the domain, you recognize a harmonic function. So it's harmonic in the domain, which allows you to integrate by parts and replace energy, which is here, into something that looks like u du dn. Okay. Then you try a minimizer, you try u plus t times some other v. Okay, I'm doing the Lagrange equation, right? And I differentiate that t is equal to 0. I say that the differential is equal to 0, and I get exactly Robin condition. Okay, trust me. If I try to do it, I will make it badly, but this is what happens, right? And again, it's done on purpose, so it's not shocking. Okay. So if you were doing the Dirichlet problem, you would not have this.
Actually, I'm a bit confused. What is cap? I mean, the point capital X does not show in the function?
Oh, no, sorry, it is.
For every X, this. I did.
So
Yeah.
this U gives you all the harmonic functions at every point. Okay. It's just the value of a function U at the point is the harmonic measure with that form. Okay. It's not too shocking, because when you change the form, the harmonic measure is a harmonic function of, it's not as if, it looks like I'm telling you a lot by saying, for every point I can compute it. It's, I have to compute this harmonic function, and this harmonic function is U. Okay. Simple question. But let's say it reassures me. It does not reassure my so much, because there are no equations. Okay. So if we were doing Dirichlet, it would be, things would be simpler. U would be 0 here, would be 1 there. It would be just minimizing this energy under some constraints, like U is equal to characteristic function of a set. It looks easier because you have this constraint, but it's harder to use because you have this strangest constraint that does not speak so well to the energy above. Okay, so you'd have to understand how the energy above is connected to the values of the boundary. Okay. And I have this comment here saying that if I am in a situation where I can define this functional, maybe there's a good chance that I can define harmonic measure. Okay, so which is reassuring to me.
Can you go back 1 second? What was the boundary value in the other formulation? I got a bit lost. So
Where?
the indicator function, here the boundary value is
Yeah.
the indicator function of phi.
So
In the previous formulation, instead.
I'll answer your question and try to move ahead at the same time. Obviously, so for a moment, I've been playing games about pretending that my domain is smooth, but I will not be interested in smooth domains. I will be interested in non-smooth domains and ugly domains. One thing that shows up in all this story is that when you have a function which has a finite energy like here, it has boundary values on d omega, so it has traces on d omega, and those traces are in L2, and you can start discussing things, and in particular, writing down those numbers, okay? So I'm saying here, there's U in the domain, and there is some guy here, which I should call trace of U, and which exists if the domain has some reasonable regularity, like NTA and plus something else, right? Am I answering another question or this one?
No, my question I think was similar. If you just can tell again what was the difference between this variation of problem and the one before in the previous slide.
No, sorry. This one is the same. I just copied.
Okay.
No, it's just that, I have a bad memory, so I assume that everyone has a bad memory, and therefore I just rewrite things the second time. So there's no difference between the two. It's okay. Okay, and then I have a comment saying that if you were interested in Neumann, so in Dirichlet, it would be this, but you would be forced to have these given values. So the integral, you don't care because it's the only thing that varies is here. And for Neumann, Neumann means A is extremely small, which means this term is multiplied by something enormous, which means U should be constant. And when U is constant, you can check the rest of the terms and find out that U should be sigma. That's because I announced earlier that this would happen. And at least in the smooth case, that's approved. Okay. Other questions? Don't hesitate. I mean, normally it's supposed to be soft, right? Okay. And in fact, I had I was not going so much ahead of myself. I'm saying that all those things here make sense if you can define a nice trace or a nice trace for harmonic functions with finite energy. And at least you can minimize this functional. You could decree that this is harmonic measure, but it's better to be able to solve the Dirichlet problem too and connect. But that's okay. Time for a statement. So let's say this is because otherwise I did not define things correctly, but it's not very important. A is an elliptic operator, and again, we've been considering that the thing was just the Laplacian. Omega is supposed to be NTA because, well, if it was not connected, for instance, you would never see the other side. Okay, so it's a fair thing to ask. And then there is this thing here, which is a way of at least allowing fractal boundaries. Okay, and you can think about less less brutal ways of saying the set is reasonable, but things are easier to say when the set is almost regular. So which means there is some measure on it, which I call surface measure, but it's Hausdorff measure of some dimension, d. And the measure of a bond is comparable to the radius of the bond through the power. So this is a d-dimensional boundary, and I'm assuming that.
And you're taking the d-dimensional Hausdorff measure of it.
And I'm
That's what you
taking,
understand as sigma.
yeah, or okay. It's I can play games, and it's better if I allow myself any alpha regular measure sigma instead of just taking constant measure.
Okay,
But
but then
for
your
the moment,
boundary condition is
the
somewhat
boundary
influenced
condition
by
will
the
be
sigma and
different.
theta, right?
No, so that's okay. So what will happen when I do this? So let's imagine that I'm taking sigma is equal to some function, let's say h, the constant measure, dimension d. Okay, and then you'll find out that when you write down the equation, I'm essentially taking my constant a and multiplying it by h of the point. So this is my way of saying, you know, there was this question, but is a constant? And I said, yes, a is constant. But since I can compensate by taking a surface measure sigma that moves, a does not need to be constant, but in this business, it has to stay bounded from below and above. Okay, okay, and then it's for the same price.
I have another question. So it's very important, as you said multiple times, to consider non-smooth domains.
Yeah.
I have no idea what's the definition of the boundary.
Indian. Aha. Okay, not yet. It will come.
Okay.
Don't wait. Don't worry. I'm thinking about it. Yeah. You can sort of guess already because I gave you a functional. So you could try to play the game by I start from functional and I try to define normal derivative so that it's it fits with it. But let's forget about it. And in fact, this is one of the things we're very proud of, which is instead of trying to approximate our set by finite length and try to see what happens when you go to the limit, it's good to allow Alphonse regular measures right away. But then, yeah, I owe you a definition. I agree. Okay, so here is a statement. With the assumptions that I was saying above, which again, the main one is non-tangential excess. And then there is the story that the measure cannot be anything at random. And I decided Alphonse regular. And maybe I did not say it and it was written somewhere. I take Alphonse regular of a dimension which is strictly between n-1, n-2 and n. So I allow codimension 1 and then 1 like this. If I take a boundary of a dimension which is too low, harmonic functions will not see it. It's not interesting. At least this way. Okay, so we're saying essentially under these assumptions, the Robin problem that I was talking about here, let's say for some continuous function f, as a unique solution. Okay. And this solution is further continuous not only on the domain, but also all the way up to the boundary. Okay. And then you can define harmonic measure, and harmonic measure is mutually absolutely continuous with respect to this surface measure that I was talking about. Sigma, and I have estimates that I will explain more on the next slide. Okay, so in other words, the situation is nice. And I have just these two comments saying that the Robin problem doesn't care about rectifiability. The counter set that I was talking about before works perfectly well. And it does not care about the regularity of the elliptic coefficients. So any elliptic matrix will give you the same result here. It does not need to be close to identity in any way, right? Which, you know, we take it as good news. You could take it as bad news because the only reason why something like this is not needed is because it's here. But anyway, that's okay. So there exist solutions, which, okay, I still need to define what to which problem. And the solutions are reasonably nice the way you would expect. So let's say in the Dirichlet problem, you would get all the way to here, this continuity as a boundary. This is called the comparison principle. But then, of course, this would become very false.
And again, your boundary condition is meant as you're minimizing that function.
For the moment, I'm saying this. For the moment, let's say that this function is defined. With the assumptions of NTA that I put, you can actually define a trace. And with this trace, you can define harmonic measure the way I said. It's a lie, but at least it gives you some definition of harmonic measure, and this one is absolutely continuous.
But then you need also some Poincaré something, no? Otherwise,
So Poincaré comes from NTA and size condition. So, yeah.
Automatically, under the assumptions of your theorem.
And yeah, you have Poincaré inequalities. Yeah, no, that's the main point. Okay, so when I think if you ask me what makes the whole machine work, the answer is I have a Poincaré inequality at the boundary. So what do I mean by Poincaré inequality at the boundary? So not only I have a trace, right? But in this bond, I have U is here. I still call it U at the boundary, and I would have something like U integral on the boundary intersected with the physical bond P of U squared is less than, let's say, the average on omega intersected with B of U plus the integral of omega intersected with B squared. And then what do I need? Absolute value here and some constants like R squared. Okay.
But that, because the dimension is bigger than D minus two.
Yeah.
I mean, it's big because it's above the capacity of.
For some reason in my mind, the bigger the boundary, the harder it was to get a Poincaré, but it's the
no.
opposite.
No.
Yes.
It's okay, so it has limitations, and again, you need to have lots of curves so that you can connect points in the domain to points of the boundary. And then there is this dimensionality thing that allows you to work this. And of course, you have better, which means that the first exponent could be different from 2 if you want.
And you probably squared the average of you, but that may be obnoxious.
Oh, and then
Otherwise, it's not homogeneous.
And then I didn't have to worry about absolute values or matrices, right? Okay, something like that. Okay, good. So
Sorry, I still didn't understand. What is then the Neumann derivative? Can you define it?
I think I'd better switch. I think I'd better switch to the normal derivative.
It's a harmonic function. So.
Okay, let me do that. You guys are too anxious. Official definition saved by no. First, what's a weak solution? Okay, and a weak solution of a Neumann of a Robin problem is something that satisfies the following thing. Okay, so it's really a weak solution of my Robin problem. So I'm defining normal derivative is equal to F in a weak way, which you're not surprised. I mean, this is the right place to. It would have been the right place to give it a weak definition immediately. But then I would have lost also my suspense. Okay, so you ask that whenever you take a test function and you compute, so this is the part which you test to get the energy typically. And then you integrate on d omega the trace times phi, okay, the trace of the function mu. Phi is supposed to be, let's say, a nice test function that is allowed to be non-zero of the boundary. So I'm doing two things at the same time. Interior, where I would take phi compactly supported in the domain and I would get harmonic. And then I allow phi to have a boundary. And right-hand side is giving you integral f against phi. And I have to say that it's true for any function, including the ones that go a little bit over the domain. Does it make sense?
But I understand if sigma is not the Hausdorff measure on the boundary, which is -1 dimensional, why is that a normal derivative? I mean, this is formally what you will do if you integrate by parts, but why do we have why should I expect such an integration by parts with a measure sigma, which is not even the surface?
Because we define weak solutions this way, and it makes sense because we have this trace in L2, which means that we still want to do integration by parts. And then what I'm saying, because what we're worried about is the integral of the notion of dudn. But in fact, what I claim matters is not dudn itself, is dudn multiplied by d sigma. And dudn multiplied by d sigma is this thing that I get here when I integrate by parts. So in other words, if you're like me and you're worried, you first take a smooth domain, and you see what happens when you're having a smooth domain. And in this case, surface measure is d sigma, and I'm really defining my thing. And then you don't object to that by integration by parts. And when I'm saying that, I think I'm saying that then if I approximate sigmas or something like this, I can go to the limit in this way.
So it's stable
So-
under taking limits, that's what you're saying?
It's stable undertaking, yeah. Or if you want, this is the reason why when I have my functional, I don't have to worry. I write down my functional and my normal derivative is exactly what comes out from my functional.
So,
Here, I'm,
so when you're saying it's stable under, let me,
but again, I mean, the
bother
main
you,
point is
a
that
bit more.
this in itself is not defined. I agree. There is no normal derivative that exists. I mean, especially on a fractal domain, but this would nicely go to a limit.
So if you take the Koch curve, for instance, and you approximate it with kind of the triangles, you're telling me that you solve the problem on the approximation.
I'm saying, yeah, if I have a function which has a derivative in L2,
Yeah.
I will be able to take a weak limit of guys like that.
Okay,
Or if you want, I can approximate that guy. The UDN, I would do it on a little box. The sigma, I would compensate by the measure of the box. It comes
We
with.
don't do it by approximation, right?
We don't do it. No,
Just if you
no,
wanted to, you would come to the same place, but we don't.
no, I understand you don't do it by approximation, but you give me a definition and
It's a definition, so you define it as a functional
Yeah,
on
no,
traces.
I mean, the
And
definition,
as such, it's, this object is, which is stable under approximation.
right, it's fine, I mean, the definition, you can give any definition you want, but
It's
the
stable
fact
under
that it's stable under
approximation.
approximation sort of motivates that you give the
Right,
definition.
but what's stable is sort of DUDN of the sigma.
Yeah, that's fine by me. So it means you take a sequence of solutions for, say, the
Yeah,
approximation
it's
of the
stable
Koch
under
curve,
approximation.
and you're actually converging to these
That's when,
objects.
yeah,
That's what you're saying.
we never do that, but we feel comfortable that we could do it.
It's not the
We do
proof,
that.
or is it the proof? Do you expect that?
What do you mean? We have only one definition. Now, if you're taking a sequence of domains, like we say, that the surface measures sigma tend to a limit, and you have weak solutions, I think we have a theorem somewhere says that
That this
is a solution.
Okay,
But at the same time, yeah. So, yeah, this is, and I should not say it's trivial because this is part of it. I mean, this is the reason why we're happy, which is that instead of taking, we like to do these things on fractals, and we have arc length on the fractal, and it becomes large, and at the same time, DUDN becomes small, and the product of the two stays more or less of the same size. And we could go to the limit. But it feels much better to just write down this and say, this is our solution, and that's the way it should be defined. And if you like, you can take your fractal, try to compute everything and see that it's the limit of. But again, we find it much more convenient to say, this is the definition, and okay, it makes sense. It makes sense because that's, again, I mean, duality is, it's important in the duality that is this product DUDN times sigma, which is important. And when the length increases, DUDN decreases, and the product stays more or less the same. Whatever. Okay.
Can I just tell you more general about this, the surface of false force regularity on a measure?
Mhm.
I mean, so first of all, is it correct to think that the sigma as a positive function type the surface measure in the simplest scenario, in the smooth case, your sigmas
Yeah.
are just bounded, and your alpha force regular means strictly positive and strictly bounded above the way.
Only above and below.
Okay.
Okay?
And then also, what does that alpha force regularity assumption between n minus n and n minus 2 open entails at the level of measure sigma as some sort of representation, or like this is what one gets in Cantor set? I'm a bit ignorant on this side.
So let's say, so for instance, it means that you can take any Cantor set of any dimension you like, strictly between n minus 1.
And this would have this assumption.
By transforming my own 1/4 there. Okay, I will get this collection of sets. They have varying dimensions. And I'm saying when you reach dimension n minus 2, okay, then bad things happen. And the bad things that happen is that the functions with finite energy don't have a trace on such a small set. Okay. But before that, they have a trace, you complete, and then you can do
So for example, you cover out the counter sets the dimension. between.
I think for the counter sets, the typical way of doing a measure on it is that there is a natural measure because you cut measure, total measure one quarter, 1 quarter, 1 quarter, 1 quarter. You subdivide and you get a natural measure on that.
Okay.
And it just turns out for regular counter sets that it's cost of measure. Okay. But nothing forces us to make regular counter sets. In fact, we have a theorem for measures that are a little bit more general than alpha regular, but we need some doubling property for the measure, and the doubling property has to put in itself this condition that the dimension has to be strictly larger than -2. That's the optimistic. Okay, so anyway, there is a, if I were doing things correctly, but then there would be a chance of getting you lost, I would have said, okay, here is the definition of weak thing. It is, of course, the same as the usual definition when the domain is smooth. And we use that all the time, and we get enough functional analysis that things work. If you yeah, so I was saying everything is nice, and I'm also saying that in the present case, in the situation where I was talking about here, the estimate that we get is better than what we had before, because harmonic measure in the ball is in fact essentially proportional to surface measure. So before there were exponents here, now we don't have them. Okay. At least this is for balls of radii, let's say less than 1. And when the radius is larger than 1, I cannot say this. I can say this, but with a constant that depends on the radius. And essentially, it's a bad estimate. So I can add a power, but the truth is that I'm getting closer and closer to the Dirichlet solution. In the case of the Dirichlet situation, we know the theorem is wrong. Okay, so it deteriorates. When you're taking larger and larger radii, the estimates get worse. But below some radius, which depend on little a, you have the two measures are proportional to respect to each other.
You mean it's wrong? It's wrong. You mean that alpha and beta cannot be taken one in the Dirichlet guides. It is
in the Dirichlet. Oh no!
It's
not only they cannot be equal to 1, but in fact, absolute continuity is false for non-rectifiable. It's much worse than that. So here we have you cannot hope for a better result. The two guys are essentially proportional. Okay. With a constant, and of course the constant depends on the radius, and it's going to tend to 1, I think, when the radius tends to 0. Okay. And yeah, thanks to Jill Pfeiffer, because we had a very, very complicated. Okay. Let me give a little bit of a proof. So again, but at some point of time, by presenting the weak solutions so badly, I can try to recuperate the story by saying that the variational thing is easier to understand. So let me give a variational proof of a mutual absolute continuity of a two measuring equation. Okay. It's unfortunately, I thought that with this thing here and quantifying everything, I would get a proof of a result. And it turns out that it's, I can't do it correctly. But there is another argument which was given to us. Okay. So remember, this is the solution. This is the minimizer of this functional. And I want to say that the two measures are absolutely continuous with respect to each other. So there is first one, which is suppose that the surface measure is 0. I want to say that the function u is 0 too, because this is the way you compute. I want to say that this number is equal to 0 everywhere at every point. Okay, so sigma v is 0. This term does not exist. If this term does not exist, I have a non-negative functional. And I know how to minimize a non-negative functional when I can try 0. So the best solution is u is equal to 0, which gives functional equals 0 and everything is equal to 0. Okay, and it's easy to see that it's the only, it's the best one that you can take. So I'm saying if surface measure is 0, then harmonic measure has to be 0. Right? If the other direction is not much harder. suppose now that I have this point here is equal to 0. So in fact, this is a harmonic function. So if it's 0 somewhere, it's 0 everywhere. So u is 0 everywhere. If u is 0 everywhere, what do I say? Sorry. If u is equal to 0, then I have the functional is, this is an optimizer. So it means that j of u for any other function u, and I'm really sorry, but there is a u here, and this is another u, and this is what I couldn't read it correctly. But I'm saying that j is a non-negative function. And if you have a non-negative functional, and you have some positive term of order 2, and some negative term of order 1, it's easy to try to minimize because you try a multiple of any solution here. And when you take a different, this is going to be multiplied by lambda squared, this is going to be multiplied by lambda. So it's very easy to optimize a function like this. And I'm saying, in fact, if you take a function u, which is a small constant, small enough, then this term here will be much larger than these terms here. Order 1, order 2, if c is small. And the functional is going to be negative, and that's a contradiction. So that's a proof of mutual absolute continuity. Right. I think it's time for me to stop almost. So there is a true proof. A true proof uses the green function estimate. I just give you the idea. If you are used to those things, you will say, yes, I was stupid, were you not to think about it before? We use the green function. There is a way to go from a green function to recuperate by a function like this. So this is a function, something that says the Poisson kernel is given by the green function. And usually the green function satisfies this, that dGdn is equal to the normal derivative of the function u should be giving you the green function. But here we have a solution, so its normal derivative is equal to a times itself. So in fact, the green function and the function u are essentially the same modulo multiplication. So in the usual case, it's very hard and complicated to estimate the green function because it's a solution of du dn is equal to something. Here, it's much easier because it's a solution of itself is something at the boundary, which gives it extra regularity, and you can use that. Okay, so the proof uses the fact that this green function is a solution, therefore it's further continuous at the boundary, and therefore we can write down the function and prove. So the main story here is that when you notice that the green function satisfies this, you're making an enormous progress in regularity. All right, yeah.
Thank you. Questions?
Do you know if there is some kind of stability between the solution of the problem and we talk about the coefficient, but the boundary of the domain. So if you find a solution for a particular domain, okay, and then you perturb in some kind of sense your domain that you want to do it, do you know what happens to the solution of the perturbed problem?
I think so. We didn't write it down, so this is the reason why I'm because I have to try to think fast. But so let's say, imagine that you're just taking a solution. My functional behaves nicely. My functional, if I change mu a little bit and so on and so forth, you have to, of course, when I'm saying this, I'm assuming that I'm having a family of domains which all satisfy uniformly my NTA conditions and so on and so forth. So I can take limits and otherwise I don't see any serious trouble unless I'm just inventing theorems right now. But I would imagine, yes, if you wanted to check, I would say first check what happens with these minimizers of this functional and try to change it. So we have some things that we check, which is that try to optimize whatever quantity in terms of a domain for the solution of the Robin problem. And then we did computation saying that when you take minutes of domains, then the solutions tend enough to the solution that this functional that we were talking about, which is the flux that goes to the limit. So we checked things like this. Some statement is true, and then it's up to you.
So let me go back to the example that I asked you. So say you take the Koch curve.
Yeah.
And then you make, one of the iterates of the Koch curve. Of course, sigma, you're not choosing it anymore, right? It's really like the one-dimensional length. So and now you're really solving the classical problem.
So yeah, so sorry.
And so your theorem is telling us, okay, so now we take the solution of the classical problem for those domains which have finite length, and we let the approximation go to the Koch curve, and actually your solution is converging to this notion of this solution. It doesn't seem a soft, because the way you were presented, like it was sort of, hinting that it's a soft consequence, but it's not a soft consequence, right? It's not a soft consequence because the length is actually converging to infinity. So it's not like the measures are converging to actually the correct measures. So there must be some subtle compensation between.
Okay. So
it has to be right. I mean, like, think about this way. If you just locally sort of look at the boundary point, just because it's a harmonic function, it means that the normal derivative on the arch that was beaten up, which is just part of the stair, should be the integral of the normal derivative, should be equal to the integral of the normal derivative on your. So it means that the normal derivative somehow has to be defined in such a way that its integral here is equal to its integral here.
So what did I write, just in case it helps? So yeah, the game you're proposing to say is that I stop my counter step at a finite step, and I get one measure, which is arc length, and its total measure is very large.
Yes.
And I try to solve this with some Robin problem with coefficient A.
Yeah, I mean, A is really fixed, right? I mean, it's a constant.
No, that's where I'm going. If you change, so you have a large measure.
Yes.
I can divide the measure by total length, and I get a measure which is a probability measure. I like it because then I can apply all my theorems.
Well, okay, then it's a soft argument. Then it's a soft, consequence that I agree, because you can pass into the functional in that case.
So now what I'm saying is that when I look at this solution that I'm thinking about, it's a Robin solution for another Robin constant, which is you multiply sigma by L, and it amounts to multiplying A by L. So if at the same time you multiply A by 1 over L, you don't change anything. So the Robin solution that you're thinking about in the limit is not the Robin solution.
It's not the
Robin solution for another A.
Okay.
And that's the way we claim it happens.
But that's because, I mean, okay, so but at that point, I would offer a piece of criticism that this is your boundary condition is not really a boundary condition on A and omega. It's a boundary condition which depends on A, omega, and the measure that you actually putting in there, right?
Yeah, although I agree.
I mean, it's so because you're telling me that, for instance, to make this approximation, you've got to change the measure to a probability measure on the boundary, which changes the constant.
Yeah, I'm saying there is an invariant, which is not obvious when I'm saying sets are
okay. Okay.
Which is that when I multiply sigma by lambda and A by 1 over lambda, I don't change anything.
But you don't change anything. Okay. Okay.
Which is one extra thing that I can use, either in the proofs or let's say in a situation like this, because I prefer probability measures. And then the price to pay to get.
No. Okay, no. Then that is why I was puzzled. So I mean, I didn't understand that you're renormalizing the measure so that you get the probability measure. And of course, you're getting something in the limit.
I'm allowed. But okay. So for instance, we've been trying to do computations to pretend that the length is really fractal. And typically what happens with the lung is that the coefficient A is very small, but the lung is fractal, so the length, the surface of the lung is very large. And either the two things compensate or not. If the two things don't compensate, you're dead because you can't breathe. Okay. And if the thing compensate, you're well. And probably if the things compensate better than it used to be, then nature was a little stupid and made your lung too complicated, and that's not worth it. So in this case, we know what the coefficient A is. We have an idea what's the small scale, and we're claiming we have to finish computations, but we're claiming should give that the lung is reasonable. But the main point is that if the lung was not fractal, it could not be able to absorb enough oxygen for you to survive. Or you'd have to move very slowly.
Just understand, if you this is a Robin measure, if you multiply the sigma by lambda, divide A by lambda is the same, and in the fixed set E is the same number. That's okay.
Yeah, because
I can't believe it. So.
You're right, that doesn't minimization function is kind of given. That makes sense.
quick solution. Put the A here, and you have A d sigma, and yeah, that's it. I mean, it's not deep. I mean, with this, I completely agree that what's unpleasant when you're thinking about prefractals is exactly this business that you always want to work with a different measure, and it's unpleasant.
No, that's fine. It's fine. I mean, if you take the I think you still actually conclude something for the problem I was telling you, because okay, so you're just telling me it's equivalent to like put a probability measure and then changing actually the constant A. Yeah. So if you just actually, I tell you, okay, keep the same constant, which means you keep the same length. Okay, then you normalize, you get the probability measure. And then the new A is actually whatever, it's exploding. So you will probably converge to kind of the Dirichlet case for the final guy. Right, I mean, depending on how you make the computation. So
everything I'm saying to you here is just a way of saying, don't get too much bothered by all those constants. You can eliminate at least one constant and get a probability.
If the example of Camillo, this A would be going to 0 because the constant we divide is larger. So we would be falling into the Dirichlet,
I think so,
measure for the limit set.
No,
but this is another
thing.
You're close to the Neumann.
No, okay. But
maybe you
but you're not converging to the Neumann measure, if that's a thing.
Well, I mean, when he minimizes the functional, for him, Neumann means it converges to a constant. So,
okay.
So then it becomes sort of trivial. But okay, so maybe we thank Guy again because